So there are three types of mirrors. There's our flat mirror, there's our concave mirror, and then here's our lesson today about the convex mirror. So you've probably seen this. In fact, I guarantee you've seen a convex mirror out in public somewhere. You've probably been in a store and you've looked up to the ceiling and you see this type of round mirror. It's like a big ball. And this is the only type of, say, mirror you're going to see out in a store like this, because what it does is it takes a really large area. You can see how large this area is in the picture, and it reduces it down to a small area. So we're taking a big picture and we're making it smaller. So that's why these ones are seen generally in stores, or if like you need to see around a corner, you might see this type of mirror. So that's the one we're talking about here, a convex mirror. Potentially as well, you probably would see these in a car, like the side windows there, because they would again take a large area and make it smaller. Now there's a spoon too. So we did talk about this the other day, that this is not the one we're on about. This is the one we're on about. So again, a large girl has had her image reduced down. Okay, so this is really just our one slide for this thing that we're gonna have to copy now. And that should say convex. Reusing slides. So how do convex mirrors form images? For an image to form in a convex mirror, again, at least two rays must intersect. We'll look at all three, but we're just looking at the two. So on a piece of paper right now, draw your mirror, and notice it's now flipped around, and draw your principal axis. Do that. Now, this is going to be a little different. We got to realize that the center of our mirror is no longer over here, right? It's not on this side anymore because we flipped the mirror around. So it's like our mirror is kind of like a big circular ball like that, right? So we have our center now right there, which means we also have our focal point right here. So our focal point is actually inside of the mirror. This is mathematically going to cause us a minor issue later on, but we just need to know that our focal point is inside of the mirror, meaning any rays that are coming in are going to get reflected through this thing. All right. Let's draw ourselves an object here. You can put this object anywhere you want. Doesn't matter. You can move it closer. You can move it further back. We're still going to have the exact same outcome. I guess I do have a website I can show you guys. I'll have to load that up after we're done, though, just to show you this. Okay, so let's do our two rays. So our first ray of light goes through, and this is exactly the same as the other day. This has not changed. So the first ray of light goes through the top of the object and through the center point. So essentially, you guys want to line it up like that, but do a better job of it. Now, our ray is hitting the mirror. Now, what's going to happen is it's going to actually bounce back on itself. What we're interested in is we are interested in the line that dots into the mirror universe. We weren't, out of our 5 scenarios the other day, 4 of them, we didn't really care about the dotted back line. It was just that very last one we cared about the dotted back line. Today we're going to care about the line that's dotting back. So this is the reflected ray here. Anytime anything's dotted, it's reflected. And I know it was reflected in this direction, but we also say it gets reflected back on itself. So that's your reflected ray. Second ray of light goes from the top of the object parallel to the principal axis, reflects off the mirror, and goes through the focal point. So here goes our second ray. It's going to go parallel. It's going to hit the mirror. So at this point, if you're drawing it, what you do is you reposition your ruler, and you would just line your ruler up. Pretend this is a ruler I'm drawing here. You'd line your ruler up Okay, that's a ruler, by the way. So you'd line your ruler up like that, and then you go about and draw your next line. Hopefully that makes sense. And here it goes. So you line your ruler up from this point and through the focal point. So it reflects off in that direction.
So the principal axis and C and F are all in the mirror world now?
Yeah. Yeah.
I think this might make things a bit harder though.
Well, there's only one outcome, so we got that going for us. Because you can see that when we dot back this ray, we've got our lines intersecting right there. Yeah, and again, to help you maybe remember that those focal points and center points are in the mirror universe is, again, it's that like pretend circle I was drawing before. You know, you got to pretend this is a circle and there's the center of the circle. The stuff we did the other day, the circle was on the other side. Anywho, those two lines have met and we've got our image. Ta-da! And the image is smaller than virtual. It's a lot closer to the mirror. What am I forgetting? And it's upright. That third line to confirm it. And this one always can be a little difficult for me anyway. So it goes from the top of the object through the focal point, then comes off parallel to the axis. And then so it's that straight line that dots back. And again, they're all kind of meeting at about the same point. So as long as you can remember the focal point and the center are in the mirror universe, then hopefully this one's straightforward. Again, there's only one outcome. Your salt properties are always going to be the same. I don't think I salted it. Yep.
So what's even the point of doing this?
I don't know how to answer that. We're gonna mix this one in with the other 5, so you have 6 scenarios now you need to know about. Okay, so let me just show you. Convex mirror interaction. And I think it's this one I've been using. Some are better than others. Yeah, here we go. So check it out. No matter where we move that thing, our image is always in the universe, the mirror universe. It's always smaller, it's always closer, it's always upright. There you go. No matter how far back you go. I guess in theory, I don't want to blow your minds here, but that image can never actually reach the focal point. As far back as you put that candle, it'll never quite reach it. Okay, so there you go. Any questions about that?
May you please go back to the PowerPoint slide? Could you please go back to the PowerPoint slide?
That one?
Yeah, that one right there. Thank you.
Okay, we got lines going all over the place here. Again, kids, remember, you just need those first 2 lines. Like I said, I prefer the green one and the blue one. To me are the 2 easiest ones. I mean, the red one's just kind of a reverse of one of the earlier lines, but I don't know. First 2 make the most sense to me. Let me know when we're good.
Yeah, we're good.
Oh, good. Any other questions? Okay. So at this point, you guys should be able to do 2 things. Hopefully, all right. You should be able to draw these with some effectiveness. And you should be able to come up with the characteristics to salting. So you should be able to salt, and you should be able to draw. When I do this in class, I also want kids to be able to measure these things. And we can get away without measuring with a ruler, but it's a really good idea, okay? Measuring these things is actually going to help us confirm our next part. So there's going to be a third thing I want you guys to be able to do. and that will be to make some calculations that back up your drawings. Now, we're going to see a couple of math equations here, and at first you're going to look, oh, I can't do that. That looks. It might look crazy at first, but it's actually a really simple equation to use once I show you how to use your calculator. It's just, it's an inverse button that we're going to use a couple of times.
You said that, like, if we saw it like in a convex mirror, it's always going to be exactly the same for every letter.
Yeah. So when I ask,
what's the point?
Well, I don't know. When I ask a question later, you'll get it right. That's the point. On your assignment that you're going to do later on, there's a question where I want you to draw and measure on a convex mirror. So hopefully you can show me that you can do that and prove it. Prove the math. How's that sound? Okay, so optics equations. So let's start off by just talking about a couple of letters, some subscripts that are going to come up in our lesson here. So you guys can just go ahead and draw a principal axis. And again, notice I've used a concave mirror for this one. Now, normally we draw the focal point and the center point in, and you can leave them in, but for this diagram, I don't want to draw them in, just because it's going to get maybe a little simplify those 2 points. That might make our lives slightly easier. So we're going to draw some stuff here with related to the object and the image. So just randomly putting the object here, there are a couple of measurements that you could make with a ruler. The first thing you can measure is you could measure how tall this object is. So you could measure that with a ruler. And the second thing you could measure is how far away from the mirror it is. Now we actually have names for these things. So if we're talking about the height of the object, we call it the HO. The H with a subscript O, the height of the object. And when we're talking about how far away our object is from the mirror, that distance, we call it the DO, the distance of the object. We've got the HO and the DO here. Now, of course, the whole point of this is to form an image and look at it. So with this one being far back, the image would actually appear here if you drew your lines properly. And just like we had a HO and a DO, we're going to be able to measure the height of this image right there. We're going to call it the height of image. And yeah, you guessed it, we've also got our distance of the image to the mirror, the die. We got the HO high and the die do. The HO do and the high die. So these are all things that if you draw a picture, you could measure. Now the other way to look at this is I can give you a mathematical question. I can give you the height of the object and the distance of the object, and I could then say calculate these two. I could say go ahead and calculate it, and with some equations we could do that. So you could always draw it, get some measurements, then you could do the calculations, and you could compare the two and see if you've done it properly or if you screwed something up. Now, even before we get to that, there's going to be some plus and minus signs that go along with some stuff today, and there's quite a nice pattern that falls out of this. So I just want to say one other thing though. So certain positions have been assigned a positive and negative value. We're going to draw those in a second here too. So what we're talking about is like the height of our object is positive in one direction and negative in another direction. And the distances of our object and our image are positive on one side and negative on the other side of the mirror. So will be, but it might be a good reference piece anyway. Okay, so draw me another axis like that. you can write this down. The height of any object or image above the principal axis will always have a positive value. So if you've got an object here and you measured it, it would be a plus number. If you added here and you measured it, it would be a plus number. If you added here and it was all of these would be plus numbers. We can't have an object on this side, but we could have an image here, right? So anytime we would have any of those, we get positive numbers. Yeah? Oh, too far. Okay. So if we have a positive height, so if the image is upright, it has a positive value. And then the exact opposite's true below the line. So if our image is pointing down, it's actually going to have a negative value. So it could be negative 2 centimeters, negative 3 centimeters, I don't know. So just put a bunch of positives above and a bunch of negatives below. And then we're going to draw another one of these on the next slide and talk about distance. Maybe you can figure that one out in advance. Ten more seconds.
Huh.
I don't think technically we could have an image over here, though, could we? I don't think that exists.
Okay, let's see. The height of plus value and minus value.
Yeah, makes sense?
Okay, that makes
Points
sense.
up, it's plus. Points down, negative. Okay, so
Could you leave it up for a little bit longer?
I guess. I can't go back now, though. Do you want me to redraw it for you? This is what it looks like. So if you got something pointing up, no matter where it is, plus. You got something pointing down, negative. Tell me when.
It's fine now.
Okay. Let's see. Yeah, there we go. Okay, so this one's distance now. And the distance of any object or image will be plus in the real world. So here's our real world, right? So it doesn't matter if the object is above or below the principal. I mean, it's always going to be above, though, frankly, right? We don't ever have objects that are starting downward. But I guess you could have an image that would be down. But anyway, the point is that anything on the left side, the real world, this is the real side, it's positive. And I'm sure you've already jumped to the conclusion that anything that's virtual now is going to have a negative value. All right, I'll leave that up there for a solid minute here. Ten seconds. So knowing what we know now, actually, I'm going to re-put up that very the hi-ho die-do, and I just want us to comment on, so this is what we started with, right? So and you can just go back and label your diagram if you want. Maybe you already understand it, that our height is positive, and the distance of our object is positive. Frankly, every scenario we draw, I think, we're going to have these both as positive, because that's how objects appear in the real world, right? They're always pointing upright. Now with our image for this one, our image was negative. It was pointing down. it was still over on the left-hand side, so it actually had a positive distance. Now, on the very next slide, I'm going to draw an important conclusion that hopefully it will help you straighten out your answers. And like I talked about there being a bit of a pattern to this stuff, this pattern, again, will hopefully help make this nice and simple. Are we good here, kids? If not, speak now.
I'm good.
Okay. All right, so here's our little conclusion. Oh, no, wait, what do we got here? Okay, so this is just another example. Let's just eyeball this. I forgot to put a couple of examples. So again, they're both positive. We got an image back here, so that would make that one negative. And it'll still have a positive distance there. So that was just a different scenario. I'll use them in another scenario. I forgot to put so many on here. Again, all three times, those two object ones are both positive. Heights. That one's still positive, but now that one is negative. Just talking about. So conclusion. Both ho and do are always positive numbers. As far as you're concerned. That's good. And one thing I've noticed over the years is that only one of the two, the high die, can be positive. So one's always positive and one's always negative. So if that's positive, or sorry, that's negative, that would be positive. And if that's positive, that's negative. So you cannot have two negative answers. You cannot have two positive answers for the high die. This is me starring this because this is an important point. So what I want to do now to wrap this up is I want us to do some calculations. I guess I haven't shown you the equations yet, so we'll take a look at these two equations. And again, don't be scared by these equations. I'll show you how to use them. They're good. There we go. Oh, sorry, I made that so tiny. There are two equations that can help us confirm the results of any ray diagram. By the way, ray diagram, that's just a fancy name for all these drawings we've been doing. They're called ray diagrams because they're diagrams and we draw them with rays. Ray diagram. Okay, so we need two equations. And the way this works is we always use this one first. Now, again, don't be like, oh, what's that? It's just a 1 over. It's again, it's just a button on our calculator. So for us to calculate, and this is what we always calculate, we want to calculate the distance of an image. Why? Because we're never given that. That's the whole point of these questions, is to draw something and figure out how far away the image is from something. So what we need to know here is, well, di is the distance of our image from the mirror. This f is our focal point or focal length. So it's like how far away from the mirror is the focal point. And again, this is all information I got to give you. Like for us to do these questions, I have to give you this and I have to give you that. And I guess I also have to give you the height of the object. There's always like those three things I have to give you. If I don't give you them, you can't do the question. So that is always going to be the first equation you want to use. And it's always the first equation you want to use because we actually need this number in our second equation. And so our second equation, what we're going to do is we're going to calculate the height of the image. So again, it's all stuff we're given with ho, the do, and we have a negative die. So we're going to be adding a negative sign in there. And I guess just mathematically, the reason is it has everything to do with what we just talked about on those previous slides. How, with the image stuff, one's positive and coming together. We learned in math at some point in our lives that multiplying two negatives together will make a positive. So the height of the image, the height of the object. We hopefully already know that. So I think a couple of examples should straighten this out. Let's do one with a concave mirror, and let's do one with a convex mirror. So instead of just giving you the mathematical problem, which is what I did, I also tried to include a drawing just so you can get an idea of what it's going to look like and maybe how to ballpark your answers. We good here? Anybody need me to leave this up? Silence means consent. Okay, so let's go. What's that? You spoke too soon or too late. Okay, so anyway, so this is like a pretty typical question. So I got to give you 3 numbers. And it's also important to know which mirror we're talking about in these questions. So a concave mirror. We're walking into the cave here. So, I don't know, maybe we can even just identify from the numbers what stuff I've given you. A 2 centimeter tall object, which is that? High die or Hodo? 2 centimeter tall, which one's that?
That would be the height of the object.
You got it. That's your hoe. It's placed 10 centimeters away. What do we think about that?
Wait, what was the first equation?
Oh.
Hold on, I took a picture, so.
Okay. I just want to know what this 10 centimeters is. Which of our unknowns is it?
Dough.
Dough. Homer says dough. And again, kids, I got to give you these 2. I have to give. These are the things I'm never going to give you the height of the image or the height, the distance of the image. Okay, I can't because that's what these are always calculating. And I also give you the focal length here, which is going to be f. So even before we get into the calculations, I think I set this up so we can see a picture of kind of what this is going to look like. And if you just want to do a quick sketch, that's cool. Now, me doing this on the computer, or anybody else doing it on this computer, you got a problem. And the problem is, how do I measure 2 centimeters and 10 centimeters? So I just kind of ballparked it here. So there's my center point. Now, how did I come up with the center point? We talked about focal length here is 4 centimeters. This, from here to here, is actually also 4 centimeters. So I think what I said in the other lesson was that the center was equal to 2f. So in this case, f was 4, so that made our center 8. But again, you need to know where the center point was. Hopefully that didn't confuse anybody when you guys did the drawings the other day for the homework. Hopefully you weren't like, oh, where's the center point? I was just trying to tell you. I didn't list it, but that's the deal here. Okay, so anyway, there's that stuff. And so there would be your object. Your object, I said about 10 centimeters here. So that's about 10 centimeters, give or take. And roughly it's about 2 centimeters tall. So again, if you got a ruler, you're probably ahead of the game here. Now, let me just see. I can't remember if I put the lines on the slide or not. No, I didn't. That's okay. Well, once we calculate it, we can go back and check. Okay, so there's our first equation. So I think it's probably a good idea to start by writing down the equation. This is always the equation you start with. And we know some of this stuff, right? We just said that is going to be f. And we said that this was going to be dough. Now, true story, when I was making up this slide, I went through the calculation, then I drew the picture, and it didn't match up. And I was like, oh, I did something wrong. I actually, when I did this, spoiler alert, was I put the wrong number. I put this 2 in that spot. Well, that was the wrong number to put there. And I would have had it wrong showing you this right now. However, because I did a double check with it, I drew it afterwards, I realized, oh, I screwed up. Okay. Now, this is where you grab your calculator, although these numbers are actually pretty easy. So we would just want to change these into decimals. Well, what's 1 divided by 4? What's 1/4 as a decimal? Oh, I spoiled it.
0.25.
0.
Yeah, 0.25. Sorry, I thought it was going to come out one at a time. Yeah, if you don't know that, you just take your calculator, you go 1 divided by 4, and you get 0.25. And then this one was probably easy too. 1 divided by 10 was
Okay, I'm
0.1.
confused here. So can I just
So-
say that I'm confused right now?
I can't hear you. What's that?
Can I just say that I'm pretty confused right now?
Yeah, you can say it. That's fine. I'm going to show you guys how to do
Okay.
this on your calculator. So we
Okay, no, wait, like, so what's DI and DO?
those are be the distance of the image. You wrote that down from the last slide. And DO is the distance the object is away. You might notice that I circled the 10 and I said, okay, it's going to act as our DO. We can complete our calculation. Again, this one's 0.25 minus 0.1 is pretty simple. It's just 0.15. But now we got a problem here. And this is where you got to get clever with your calculator. I'll show you guys in a second how to use the calculator. We want to know what distance of the image is. Right now, this isn't in terms of distance of image. It's 1 over the distance of the image. So we have to do a little mathematical move. In fact, all we kind of do, and this isn't really accurate, but what we're doing is we're just kind of moving this 1 over to the other side. So our distance of our image is equal to 1 divided by 0.15. This is where we need a calculator. Because personally, I don't know what 1 divided by 0.15 is. Maybe somebody with a calculator could shout it out, though. What is 1? What's 1 divided by 0.15? I can wait here all day, kids. 1 divided by 0.15.
0.66.
6.66? I think somebody said 6.66. It is. Bam.
4.
Now, I am going to, I got to stop the recording here just so I can go to the internet and show you that calculator. This might have been one of the easier ones because we may not have needed a calculator to do these conversions here. Sometimes you do. So I'll go show you what to do if you got to do the whole thing. Okay, so let me stop and then I'll come back. So by the way, if you don't have a calculator handy, check this out. You open up a new browser and you can type the word calculator in, or you can just type 9 times 9 and hey, it does math for you and a calculator comes up. Look at that. So go to Google, type in 9 times 9 or calculator, and you get the old calculator. So if you had to actually calculate this question, the original question was 1 over 4 minus 1 over 10. So watch this. So we go 1 divided by 4 equals 0.25. Then we're going to subtract the 1 divided by 10. And it gives us our 0.15. And now we just want to go 1 divided by 0.15. So 1 divided by 0.15, or answer button. You get 6.67. That's it. Done. Hopefully that's not too difficult. Want to see that again? 1 divided by 4 equals, subtract 1 divided by 10 equals, that's not our answer, because we have to go 1 over our answer, 6.667. We'll make a drawing. We'll see, does that number actually make sense here? Where's my PowerPoint? Okay, there it is. How are we feeling about that?
Good.
Hopefully not too bad. Okay, so I just did a quick, you don't need to draw this, but this is what it would look like. And so if you got out your ruler, you'd say, okay, from here to here, that would be 6.67 centimeters. Now, spoiler alert, it looks like our height is going to be negative. We're going to calculate that next here. All right, I don't care if you copied that down, it's fine. Oh, yeah, there it is. Height will be negative. Distance will be positive. Oh, wait a minute, I didn't actually do the height. Hang on a sec. Did I forget to do that? Hang on. Oh, no, I skipped it. Sorry, that's what happened. Sorry, I missed a slide there. Okay. Okay. Now we've seen that a bunch of times. Okay, sorry, this was a slide I missed. So the next thing you got to do is you got to calculate the height of the image. We need this formula. Now we already are given two of the numbers, the hoe and the dough. And from the last question, we just calculated this to be 6.67. Now there is a negative sign we're going to introduce here in a moment, and that's fine. So, this one I think is simpler to use, frankly. You're just plugging numbers in. Our hoe was 2. Our dough was 10. And then this is going to be negative 6.67. Not to spoil it, but there's our hoe as 2. There's our negative die, negative 6.67. And then there is our height. So I guess if you're smart, this number's still on your calculator, because you just need to make it negative. And then you just multiply it by 2 and then divide by 10. And if you do that properly, you get negative 1.33. So hopefully the height's a little easier to calculate. Hopefully that doesn't blow your mind too much.
Oh God, I really don't know what's going on.
Well, I'll just copy it down so you can look at it again and you can watch the video again. We've got some practice questions later. You can do those. Can I move on here, kids? Anybody?
Sure.
Okay.
Sure.
Awesome. Okay, so this was a slide I guess I accidentally showed too soon. There was our image, and then we measured our height, and it's pointing down, and it's negative 1.33. And then there's the distance of our object, and that was the positive value. Okay, so second question. This one's convex, so this is what we did today. So change the numbers slightly. Hopefully in your minds you got a picture of what this is going to look like, because there's only one outcome. So we're going to be taking our object and we're shrinking it down. And there's going to be one little complication as well too as we go along here. And that's now that our focal point is inside the mirror. So we'll adjust for that in a second. So there's our center point. There's our object. And yeah, this is kind of what it's going to look like. Again, I did my best to sort of ballpark it. So I tried to put it 12 away. And then that was 6.
Okay, so what do we? So the equation, 6
Yeah.
centimeters.
Yeah. So
calculate its HI and DI.
Yep. So there's our hoe and our dough, and our F.
So the I is great. I keep forgetting.
Yeah, the I is the image. So the image isn't on here yet. Yeah. O for object, I for image.
So what's D and I? D and H?
Which one? There's 2 of them.
Like D.
D is distance from the mirror, and height is how tall it is.
So the image is height, and
Yep.
the image is distance. Oh, okay.
Yeah, no, not O, I, image.
Yeah, the image is distance from the mirror,
Yeah.
and
Yeah, exactly.
yeah, thank you
Okay.
so much.
Yeah, no worries. Yeah, it takes a little bit of time to catch on to this stuff. I know the first time I think I taught it, I was like, what's going on? But then I realized, hang on, there's some patterns here that fall out here. Okay, so again, we always want to calculate the distance of our image first, but there's a kicker to this one. And it has to do with this convex mirror. It has to do with, that was the wrong line. It has to do with our focal point being over here. If we just were to proceed and do our calculations using this equation here, we get the wrong answer. It wouldn't work out. We get a wrong sign. So we actually have to add just one little thing to this. We have to add an extra negative sign right there. So both of these terms are now negative. And why is it negative? It's negative because our focal point is inside. So only for convex are we going to do that. So it's that extra little thing. And again, it just becomes plugging numbers in, right? So there's our focal length. And there is the distance of our object. So our answer is going to be negative here, right? Because both these terms are negative. We're just adding negatives together at this point. So again, this first one should be easy because, you know, it's negative a quarter. 1 divided by 12. I don't know, it's probably like 0.83 or something. I don't know, I'd have to grab my calculator. And I'll do it for you guys in a second or two. Oh, I was right. Look at that. Because it helps to have created this slide. So 1 over di equals, again, those two terms are just, you know, grab your calculator, figure them out. They're both negatives. So we're just adding up negatives at this point. And it actually goes together quite nicely. Look at that round number, if you will. Negative, it's a negative there. Negative 0.3333. Negative a third. And again, that's not our final answer because we still got this 1 over problem. So you kind of just put it over on this side. It's not mathematically correct the way I'm saying it, but it works, so do it. So this is where you grab your calculator and you go 1 divided by 0. Very negative. You need negative in there. Negative 1 divided by 0.333. So 1 over a third. How many thirds are in 1? I think it's like 3. Negative 3? Oh, negative 3. Good guess. Again, kids, I'll grab the calculator in a sec and show you how to do that. Again, now we're on to the second. Now that we're on to the second example here, hopefully this step just gets to be repetitive. Again, I know it looks a little confusing, but it's just you're just dividing 1 every time. 1 divided by a number. 1 divided by a number.
What's F again?
F's your focal length. So that's like when you draw the picture, your focal length. That's how far that F is away from the mirror.
So I guess this math shouldn't be too hard.
Hopefully not. Again, just grab a calculator. We'll do the we'll do the height next before we. Can I move on here? Anybody need this?
Wait, excuse me.
Okay.
So since it's a convex mirror, it has to be negative?
Yeah, focal length is negative. Again, because that focal point.
Because the convex mirror.
Yeah, so the convex always has a negative focal point because it's inside.
Thank you.
That's the only thing you gotta be careful of. Okay, so we'll wrap this up here, and then I'll go back to the calculator and show you once. It's probably easier if I stop the video to do it. At this point, it's just plugging stuff in. And this is a scenario where we get 2 negatives. Now think about this. If you can picture the result in your mind, the image is upright. I don't know if you remember that from earlier. It's upright, so that means our answer has to be positive here. I don't know why I rewrote the equation there, but there it is. Probably don't need that. So our HO would be 6. Now, we just calculated the DI on the last slide. And remember, we calculated it to be negative 3. So this is where we're going to get two negatives in a row. So it's like saying negative, -3. Now I do want to simplify that though. So you can write that down, but we're just going to erase it in a minute because two negatives make a positive. So let's just say it's 3. Let's not say it's and our negatives are now gone. This is going to give us a positive answer. 18 divided by 12, 1.5. And yeah, hopefully again that makes sense. If you've done the drawing, you look at it, you're like, well, the height's positive. It's got to be positive. So you got to be careful of those negative signs there. So the calculations might seem a little more difficult. But again, the point of them is to check our drawings. You've done the drawing. You should be able to at least, use a website or something to confirm your drawing is correct.
Okay, let's see. HI, the height of the image, equals the height of the object times the negative distance of the image.
Yep.
And then we divide that product by the distance of the object.
Yeah. So that's what it sort of should look like here. And I think I went about and did it. Hey, I did. Look at that. So draw this one. This is what we learned earlier today. Bam. Draw that. One towards the center. Booyah. And you put your image. And that should check out, right? Because we said that the height of the image was a positive number, whatever it worked out to be. And we're inside of our mirror universe, so that has to be a negative. And again, we said earlier that one's always positive and one's always negative. I like this stuff only because there shouldn't be any surprises with the math. It might be a little confusing, but at least we've got a few things to go back and double check and see if we're actually doing it properly. No swearing, please.
Also, could I, Mr. B?
Yes?
Can I tell you something that's completely unrelated to what we're doing?
Not yet.
Okay.
I just want to, and this was the last slide, but I just want to jump to the calculator and just do that one calculation to show you guys again. Let's see here. So back here, it was -1/4 minus -1/12. So if I was going to type that in, I guess I could say -1 divided by 4 equals that, and then I'm going to subtract 1 divided by 12. And there's our negative answer. And then I'm going to divide that by 1. So let's go 1 divide by, I'm just going to use the answer button here, kids. That's the beauty of this one. I think if you use Explorer, a different one, then there isn't an answer button. Anyway, boom, there's our -3. So that was the distance of our image. Okay, so a little practice here. So I want to show you something. This is our now work. That's the note we just did. Here are the mirror drawings and calculation sheet. Notice there is a due date on this. These are the drawings we started on Friday. So if you did the work over the homework, or if you did the homework over the weekend, you're halfway there. You've already done the drawings. If you didn't do it, then you've got twice as much work to do. By the way, almost every lab is in. There's only like 5 kids that didn't do it. I'm going to mark those soon. So let me just open this up here. I chopped the first 3 questions off because the first 3 questions had nothing to do with drawings. So questions 1, 2, 3, and 4, these were like questions 4, 5, 6, and 7 from the other day. So they're the exact same dimensions. However, I have added in the fact that I want you to do the calculation. So if you've already done the drawings, again, I don't really care how you do this. If you've already done the drawings, maybe you can do the calculations nearby on the piece of paper. I have added one extra one. So the first 4 are all concave, 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 and then this one's convex. So it's just like that one calculation we just did. So I want you guys to manufacture me this piece of work. I want it by Friday. We're done with this stuff though. We're moving on from here. And I want you to upload this to our assignment area right where you guys uploaded the double displacement lab. So I just made another spot for you to upload it. And this assignment's it's weighted as a 1.5, so it's weighted as much as the lab, and it's more than the quizzes we've been doing. And yeah, so in terms of handing it in, I guess there's a couple of ways. Firstly, if you could scan it using a printer or something and turn it into a PDF, I guess that's probably best for me. Your second default is just to take a picture of it and upload the picture, or even email me the picture, because I can just look at it and you know, I can just look it over. Just make sure it's a decent quality picture. That's probably about it. I mean, I wouldn't recommend sort of doing this on a computer. I mean, you could, but I don't know. I don't know if you want to do that.
Excuse me?
So this and the other drawings. So I don't want the other drawings. So Logan, I just want these 5 drawings, and you've already done 4 of them. That's what I'm telling you. And then the calculations to go with. So yeah, that's the plan.
Excuse me?
Yes.
Do you just want us to do the equations, or do you want us to draw a graph afterwards?
So it says on here, I want you to draw.
Oh, draw a ray diagram. Okay, thank you.
Yeah. Yeah. So draw your ray diagram and then do your calculations.
Thank you.
Yeah. So you guys can start on this now. Like I said, this is it. However, I'll preface this with a however. However, I think it's Thursday and Friday, we're looking at lenses. So right now we're dealing with mirrors, right? Mirrors reflect. Well, lenses, light passes through. But here's the awesome thing, that all of these calculations and all these scenarios also apply to our lenses. So this is going to be like recalled in a couple of days. So I'd like us to at least master it right now. And yeah, if you get any questions, feel free to ask me. Again, I know this is like the first time we're doing it, and I'm already asking us to hand something in, but that's sort of the nature of this course.